Now, in this lecture, we'll answer on two questions. In the first question, we'll find out the radius of this circle that is inscribed by triangle ABC. In the second question, we'll find out the area of rectangle ABCD that blocks this circle. Okay, we'll start with the first question. In the drawing, we have triangle ABC. Side BC equals to 2 units, angle ABC equals to 60 degrees, angle ACB equals to 75 degrees. Inside triangle ABC we have a circle that is described by the triangle, and our mission is to find out the radius of this circle that is described by triangle ABC. So we'll start with the first method, and from point C we'll go perpendicular on AB. So this angle equals to 90 degrees, and this angle is also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB is D. In the next step, I will copy the right triangle DBC in a new page, and we analyze triangle DCB. Okay, so here so this is the right triangle DBC that I copied from the original drawing. In the right triangle DBC, the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have inside triangle DBC? We have this angle that is equal to 60 degrees plus this angle that is equal to 90 degrees plus the missing angle that will define as angle X. In total, the sum of those three angles must be equal to 180 degrees. So 90 degrees plus 60 degrees is 150 degrees plus X. In total, it must be equal to 180 degrees. Here, we subtract 150 degrees from this equation, and we get that the missing angle X equals to 180 degrees minus 150 degrees. It is equal to 30 degrees. So this angle equals to 30 degrees. And right here also that this angle equals to 30 degrees. So we continue to focus on the right triangle DBC. In the right triangle DBC, it is very easy to see that sinus 30 degrees is equal to dB over BC. Okay. So it is dB over BC, but BC equals to 2 units according to what is given us in the question. So we substitute BC by 2. Sinus 30 degrees is 1/2. That is equal to BD over 2. Here we will multiply this equation by 2 and we will get that BD equals to 1 unit. Here BD equals to 1 unit. So we can write here that BD equals to 1 unit. We continue to focus on the right triangle, triangle DBC. In the right triangle, triangle DBC, cosine 30 degrees, is equal to DC over BC. Okay, so cosine 30 degrees is square root of 3 over 2, and it is equal to DC over BC, but BC is 2, so we substitute BC by 2, and we'll get that square root of 3 over 2 equals to DC over 2. We'll multiply this equation by 2, and we get that DC equals to square root of 3 units. So here DC equals to square root of 3 units. What is the size of angle ACD? The size of this angle ACD, is equal to the size of the big angle, that is angle ACB, that is equal to 75 degrees, minus angle DCB, that is equal to 30 degrees. Therefore, 75 degrees minus 30 degrees equals to 45 degrees. So angle ACD equals to 45 degrees in its size. In the next step, I will copy the right triangle ADC in the new page, and we will analyze triangle ADC. So this is the right triangle ADC that I call it from the original drawing. The sum of the angles in this triangle ADC must be equal to 180 degrees. So which angles we have inside triangle ADC? We have this angle that is equal to 90 degrees, plus this angle that is equal to 45 degrees, plus the missing angle that will define as angle X. In total, the sum of those three angles must be equal to 180 degrees, according to the rule that the sum of the angles in a triangle is equal to 180 degrees. So 90 degrees plus 45 degrees is 135 degrees, plus X. In total, they must be equal to 180 degrees. Here we subtract 135 degrees from this equation, and we get that the missing angle X, is equal to 180 degrees also 135 degrees. It is equal to 45 degrees. So this angle equals to 45 degrees. We continue to focus on the right triangle ADC. In the right triangle ADC, those two angles are equal to each other, they're both equal to 45 degrees, therefore they're equal to each other. And we have the rule that in front of equal angles in the triangle, there are equal sides. So in front of this angle, we have side AD. In front of this angle, we have side DC, and those two sides must be equal to each other because they are located in front of equal angles. So AD equals to DC. But we have already found out that DC equals to square root of 3 units. So from this equation, AD equals to DC equals to square root of 3 units. We will derive that AD is also equals to square root of 3 units. Okay, here AD equals to square root of 3 units. And here also we can write down that AD equals to square root of 3 units. In the next step, we'll implement the Pythagoras theorem on the right triangle, triangle ADC. So in the right triangle, triangle ADC, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AC squared equals to AD squared plus DC squared. So AC squared equals to AD squared. AD equals to the square root of 3 units, therefore AD squared is square root of 3 squared, that is 3, plus DC squared. DC is equals to the square root of 3, therefore DC squared equals to the square root of 3 squared, that is also 3. So AC squared equals to 3 plus 3, that is 6. So we take out of this equation, equation number 1, and we'll get that AC equals to the square root of 6 units. Here, AC equals to the square root of 6 units. So actually, we found out the lengths of all the sides of triangle ABC. So now, I present to you a new rule, and we will implement the new rule in our triangle, in our drawing. So here, according to the new rule, the radius of any circle that is inscribed by triangle ABC, that could be any triangle, the radius of this circle R will be equal to the area of triangle ABC over the semi-perimeter of triangle ABC. And the semi-perimeter of triangle ABC equals to the perimeter over 2. Side AB equals to a unit, side AC equals to 3 units, and side BC equals to 3 units. Therefore, the semi-perimeter of triangle ABC will be equal to the perimeter, that is A plus B plus C over 2. Okay, so we implement the new rule in our drawing. So here, the radius of this circle, according to the new formula, will be equal to the area of triangle ABC over the semi-perimeter of triangle ABC. Okay. So the area, the radius of this circle that is inscribed by triangle ABC will be equal to the area of triangle ABC over the semi-perimeter of triangle ABC. The area of triangle ABC will be equal to the base of the triangle times the height over 2, times the height to the base over 2. Okay, so we take the base of triangle ABC as AB. The height to the base AB will be DC over 2. So in conclusion, we found out that the area of triangle ABC equals to the base AB times the height to the base, that is DC over 2. So here, AB, the base AB equals to 1 plus square root of 3 units. DC equals to square root of 3 units over 2. Okay, so the area of triangle ABC equals to 1 plus square root of 3 over times 3 times square root of 3 over 2. The value of this expression is equal to 2.366 square units. So you can write down that the area of triangle ABC is equal to 2.366 square units. What is the value of the semi-perimeter of triangle ABC? The semi-perimeter of triangle ABC equals to the perimeter over 2. The perimeter of triangle ABC equals to AB plus AC plus BC over 2. Okay. So the semi-perimeter of triangle ABC equals to AB is equal to 1 plus square root of 3 units, AC equals to square root of 6 units, and BC equals to 2, all divided by 2. Okay, so the semi-perimeter of triangle ABC equals to 1 plus square root of 3 plus square root of 6 plus 2 over 2. So the semi-perimeter, the value of this expression is 3.59 units. So in conclusion, we found out that the radius of this circle that is described by triangle ABC, it is equal to the area of triangle ABC over the semi-perimeter of triangle ABC. And the area of triangle ABC is equal to 2.366 square units over the semi-perimeter of triangle ABC, that is equal to 3.59 units. And 2.366 over 3.59 is equal to 0.6589 units. So the radius of this circle that is inscribed by triangle ABC is equal to 0.6589 units. Okay, so we finished with the first method. In the next step, I present to you how to find out the radius of this circle that is inscribed by triangle ABC according to the second method. Okay. So in the second method, we define the center of the circle as point O. We will define the point of tendency of tangent BC with this circle as point D. We'll join points O and D together by a straight line. Point O is the center of the circle, point D is the point of the circle itself, therefore OD is the radius of the circle that we will define as R. And we have the radius OD that is drawn to the point of tendency. Therefore, according to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. We join points O and C together by straight, O and B together by straight line. We join points O and C together by straight line. We will define the point of tendency of tangent AB with this circle as point E. We define the point of tendency of tangent AC with this circle as point F. We join points O and E together by a straight line. Point O is the center of the circle, point E is the point of the circle itself, therefore O is the radius of the circle that is equal to R. Likewise, but before that we have here the radius OE that is drawn to the point of tendency, therefore this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. We join points O and F together by a straight line. Again, point O is the center of the circle, point F is the point of the circle itself, therefore OF is the radius of the circle that is equal to R. And also we have the radius OF that is drawn to the point of tendency, therefore this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. In the next step, I will present to you rule number 2, and we will implement rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from common external point to a circle are equal. So we have the common external point P. From the common external point P, we have tangent PB, and we have also tangent PA. The lengths of those two tangents are equal to each other. This is to say, PA equals to PB. Okay, so here we can implement rule number 2 in our drawing, because in our drawing we have the common external point B. From the common external point B, we have tangent BD, and we also have tangent BE. The length of those two tangents must be equal to each other according to rule number 2, that is to say, BD is equal to BE. Likewise, we have the common external point C. From the common external point C, we have tangent CD, and we also have tangent CF. And according to rule number 2, the lengths of those two tangents must be equal to each other. That is to say, CD is equal to CF. In the next step, we will prove that the green triangle OBD is congruent to the orange triangle OEB. So, why the green triangle is congruent to the orange triangle? So I write it down here. We prove that the green triangle that is actually triangle OBD is congruent to the orange triangle that is actually triangle OBE. So, why those two triangles congruent to each other? First of all, we just right now found out that side BD of the green triangle is equal to side EB of the orange triangle according to rule number 2. So BD is equal to BE according to rule number 2. In addition, DO equals to OE, they are the area of the circle that is equal to R. And finally, side OB is the common side that belongs to both triangles, so side OB equals to itself. So we actually proved that the green triangle is congruent to the orange triangle according to side rule. So I write it down. The green triangle, triangle OBD, is congruent to the orange triangle, triangle OBE, according to side rule. And from the fact that those two triangles congruent to each other, we conclude that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So here we can write down that angle OBD is equal to this angle, that is actually angle OBE. Okay, angle OBD is equal to angle OBE. So if we define angle OBE as alpha, then from this equation angle OBE equals to angle OBD equals to angle OBE equals to alpha, we will derive that angle OBD is also equals to alpha. So both those two angles are equal to alpha. And we know that the sum of those two angles, that is alpha plus alpha, must be equal to 60 degrees according to what is given as the equation. Alpha plus alpha is 2 alpha, and 2 alpha equals to 60 degrees. Here we divide this equation by 2, and we get that alpha equals to 30 degrees. So actually found out that alpha equals to 30 degrees. So here, this angle alpha equals to 30 degrees, and this angle alpha, it is also equals to 30 degrees. Okay. Actually, it is also the same process here. Will not repeat of the same process. Those two triangles are also congruent to each other according to side rule. Therefore, those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So you can write down that angle FCO, this angle, is equal to this angle, that is actually angle OCD. Angle FCO equals to angle OCD. According to the rule, the corresponding angles in congruent triangles are equal to each other. So if we define angle OCD as theta, then from this equation we will derive that angle FCO is also equals to theta. So those two angles are both equal to theta, and the sum of those two angles is theta plus theta, this is 2 theta, and 2 theta must be equal to 75 degrees according to what is given as the equation. We divide this equation by 2, and we get that angle theta is equal to 37.5 degrees. Angle theta equals to 37.5 degrees. So this angle theta equals to 37.5 degrees. And this angle theta, it is also equal to 37.5 degrees. So in the next step, we will focus on the green right triangle, triangle OBD. In the green right triangle, triangle OBD, it is very easy to see from the drawing that triangle is 30 degrees is equal to OD over BD. tangent 30 degrees equals to OD over BD. OD equals to R, so we substitute OD by R. So in conclusion, we found out that tangent 30 degrees equals to R over BD. Tangent 30 degrees equals to R over BD. Here we multiply this equation by BD and then we divide it by tangent 30 degrees, and we get that BD is equal to R over tangent 30 degrees. BD is equal to R over tangent 30 degrees. In the next step, we'll focus on the yellow triangle ODC. In the yellow triangle ODC, it is very easy to see from the drawing that tangent 37.5 degrees is equal to OD over DC. Okay. So tangent 37.5 degrees equals to OD, but OD is equal to R, so we substitute OD by R over DC. So in conclusion, we found out that in the right triangle ODC, tangent 37.5 degrees equals to R over DC. Here we multiply this equation by DC and then we divide it by tangent 37.5 degrees. And we get that DC is equal to R over tangent 37.5 degrees. So actually we found out the values of DC and also the value of BD. And what is the value of side BC? From the domain it is very easy to see that BC equals to BD plus DC. Again, BC equals to BD plus DC. So write it down. BC equals to BD plus DC. Yep, BC equals to BD plus DC. So BC equals to BD. BD, we already found out that BD equals to R over tangent 30 degrees plus DC. We just right now found out that this equals to R over tangent 37.5 degrees. And we know that BC is equal to 2 units. Only what is given as the question, so we substitute BC by 2. So 2 equals to, here we take R as a common factor out of those two expressions. So what is left from R over tangent 30 degrees after we took from it R as a common factor? What is left is actually 1 over tangent 30 degrees. And what is left from our rectangle is 37.5 degrees after we took from it our second factor. What is left is actually 1 over tangents 37.5 degrees. So 2 is equal to R. 1 over tangents 30 degrees is equal to 1.372 plus 1 over tangents 37.5 degrees is equal to 1.303, and here 2 equals to R, and 1.732 plus 1.303 is equal to 3.3 3.035. Okay, here we will divide this equation by 3.035, and we'll get that 2 over 3.035 is equal to the radius, and 2 over 3.035 is equal to 0.6 0.68 actually it is 0.589 units. So the radius of the circle equals to 0.658 0.6589 units. Okay, so we finished with the first question. In the next step I will present to you the second question, and we solve the second question in 2 different methods. In the drawing we have rectangle ABCD. Inside rectangle ABCD we have the circle that is inscribed by rectangle ABCD. Chord PS equals to 6 units in its length. Line segment SQ equals to 5 units, and our mission is to find out the area of this rectangle ABCD. Okay. So first of all, we know that all the angles inside the rectangle are right angles, so this angle equals to 90 degrees, this angle equals to 90 degrees, this angle equals to 90 degrees, and finally this angle, it is also equals to 90 degrees. Okay, we define side AB as A. We define side BC of rectangle ABCD as B, and BC is also the diameter of the circle, so I write it down. We define the center of the circle as O. We join points P and O together by a straight line. Point O is the center of the circle. Point P is the radius, is the point of the circle itself. Therefore, OP is the radius of the circle that we will define as R. And we already found out that the diameter of the circle is B. So if the diameter is B, it means that the radius must be equal to half of it. That is to say, the radius of this circle will be equal to B over 2. So R equals to V over 2. Okay. So here we have the radius OP that is drawn to the point of tendency. Therefore, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1, that the tangent to a circle is perpendicular to the radius 1 to its point of tendency. In the next step, I will present to you rule number 4, and we will implement rule number 4 in our drawing. According to rule number 4, the perpendicular from the center of a chord, the perpendicular from the center of a circle to a chord bisects the chord. The perpendicular from the center of a circle to a chord bisects the chord. So here the center of the circle is at point O, and we have the perpendicular OM. According to rule number 4, the perpendicular OM bisects chord CD. That is to say, CM equals to MD. According to rule number 4, here the perpendicular OM bisects chord CD. Therefore, CM equals to CD. We can implement rule number 4 in our drawing. From the center of the circle, that is point O, we draw perpendicular on chord SP. Okay. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And we define the touching point of the perpendicular from point O and SP as M. And according to rule number 4, the perpendicular OM bisects chord SP. That is to say, SM equals to MP according to rule number 4. So if we define SM as X, here SM equals to X, then for this equation X equals to SM equals to MP, we will derive that MP is equal also to X. Here MP equals to X. Okay? And SM is X and MP is X. So X plus X will be equal to SP. X plus X equals to SP. X plus X equals to SP. X plus X is 2X, that is equal to SP. But it is given as the equation that SP equals to 6 units. So from this equation, 2x equals to SP equals to 6, we derive that 2x is equal to 6. Here we divide this equation by 2, and we will get that x equals to 3. Here x equals to 3, x equals to 3, and here also x equals to 3 units. Okay, so here we'll define the point of tendency of tangent DC with this circle SF. We'll join points O and F together by a straight line. Point O is the center of the circle. Point F is the point of the circle itself. Therefore, OF is the radius of the circle that is equal to R. And we have the radius OF that is going to the point of tendency. Therefore, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. So inside quadrilateral OPSCF, we have 1, 2, 3 right angles, and any quadrilateral that has three right angles, the fourth angle must be also equal to 90 degrees in order to complete the sum of the angles in this quadrilateral to 360 degrees. This angle must be equal to 90 degrees. Okay, so in the next step, we'll do a construction from point Q. We'll draw perpendicular on BC. Again, from point Q, we'll draw perpendicular on BC. So here, so this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We'll define the touching point of the perpendicular from point Q and BC as T. We will define the intersection point between sides Q, between the perpendicular QT and the radius OF as H. So here, by doing this construction, we created here quadrilateral OPHT. Again, we have here quadrilateral OPHT. Inside quadrilateral OPHT, we have 1, 2, 3 right angles. Therefore, the fourth angle, this angle must be also equal to 90 degrees. So I already explained to you, this angle must be also equal to 90 degrees. So inside quadrilateral OPHT, we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral OPHT as a rectangle. Why? Because it has 4 right angles. Repeat again. This quadrilateral OPHT is a rectangle. And we know that the opposite sides of a rectangle are parallel to each other. That is to say, side OP must be parallel to side HT. OP is parallel to HT. Okay, OP rectangle OPHT, OP is parallel to HT. But HT is part of the perpendicular QT. HT is part of the perpendicular QT, and QT as a perpendicular, it is absolutely a straight line. So I can write down here that QT is a straight line, it's a perpendicular. QT is a straight line, repeat again, QT is a straight line, and HT is part of the straight line QT. From the drawing, it is very clear that HT is part of the straight line QT, and HT is parallel to OP. So part of the straight line QT is parallel to OP. Therefore, the straight line itself QT must be also parallel to OP. So I write it down that QT must be also parallel to OP. QT must be also parallel to OT. Why? Because if part of the straight line QT is parallel to OP, then the straight line itself QT must be also parallel to OP. Okay, and here we have rule number 9, that alternating angles between parallel lines are equal to each other. According to rule number 9, alternating angles between parallel lines are equal to each other. Here, line A is parallel to line B, and we have those two pink angles are defined as alternating angles, and they are located between the parallel lines A and B. Therefore, they are equal to each other. Okay, we can implement rule number 9 in our drawing, because in our drawing we have those two angles that are defined as alternating angles, and they are located between the parallel lines OP and QT. Therefore, they are equal to each other according to rule number 9. So I write it down. Angle OPM, this angle OPM is equal to this angle, that is actually angle PQT. Repeat again, angle OPM is equal to angle PQT according to rule number 1, according to rule number 9, because of the fact that those two angles are alternating angles and they are located between the parallel lines OP and QT. Therefore, they are equal to each other according to rule number 9. So if we define angle PQT as theta, this angle PQT equals to theta according to our definition, then from this equation angle OPM equals to angle PQT equals to theta, we derive that angle OPM is also equals to theta. Angle OPM is also equals to theta. This angle OPM is equal to theta. In the next step, we'll focus on quadrilateral QTCD. This quadrilateral. Inside quadrilateral QTDC, we have 1, 2, 3 right angles. Therefore, the fourth angle, that is to say this angle, must be also equal to 90 degrees. So actually, inside quadrilateral QTDC, we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. Therefore, quadrilateral will relate to quadrilateral QTDC as a rectangle. Okay? And we know that the opposite sides of a rectangle are equal to each other. That is to say, QT is equal to DC. QT is equal to DC. QT is equal to DC according to the rule that the opposite sides of a rectangle are equal to each other. But we know that ABCD is a rectangle and the opposite sides of a rectangle ABCD are equal to each other. That is to say, DC is equal to AB. DC is equal to AB in rectangle ABCD. And for this equation QT equals to DC equals to AB, we will derive that QT is also equals to AB. QT is also equals to AB. But according to our definition, AB equals to A. AB equals to A. So can I tell that AB equals to A? And from this equation, QT equals to AB equals to A, we will derive that QT is also equals to A. QT is also equals to A. So we can write down that here that QT is equal to A. In the next step, I will copy the right triangle, triangle OMP in a new page and we'll analyze triangle OMP. Okay. Angle MPO equals to theta. Side MP equals to 3 units, and the hypotenuse OP equals to B over 2. It is the radius of the circle. It is equal to the radius of the circle, that is B over 2. So this is actually the right triangle OMP that I copied from the original drawing. In the right triangle OMP, it is very easy to see that cosine theta equals to MP over OP. Again, cosine theta in the right triangle OMP equals to MP over OP. So I write it down. So here MP equals to 3 units, we substitute MP by 3, and OP equals to B over 2, so we substitute OP by B over 2. So here we have 3 over B over 2, we'll move 2 to the numerator, 2 times 3 is 6, we'll move B to the numerator, so we get that here it is 6 over B. So in conclusion, we found out that according to equation number 1, cosine theta equals to 6 over B. Okay. Cosine theta equals to 6 over B. In the next step, we'll focus on the right big triangle, triangle PQT. In the right big triangle, triangle PQT, cosine theta. What is the value of cosine theta? It's very easy to see. From the drawing, that cosine theta equals to qt over qp. Okay, cosine, I repeat again, in the right big triangle QPT, cosine theta equals to QT over QP. We have already found out that QT equals to A, so we substitute QT by A. And what is the value of QP? QP equals to 5 plus 6. Again, QP equals to 5 plus 6. This is 11. So we substitute QP by 11. So in conclusion, we found out that cosine theta, according to equation number 2, equals to A over 11. Okay, according to equation number 2, cosine theta equals to A over 11. So we have two different expressions for cosine theta, therefore we get equation number 3 that states that cosine theta according to equation number 1 must be equal to cosine theta according to equation number 2. And cosine theta according to equation number 1 is equal to 6 over b. It must be equal to cosine theta according to equation number 2, that is equal to A over 11. Okay. So in conclusion, found out that according to equation number 3, 6 over b equals to A over 11. Here we cross multiply this equation number 3, and we get that according to equation number 3, A times B is equal to 6 times 11, that is 66. So AB equals to 66 according to equation number 3. And what is the area of rectangle ABCD? The area of rectangle ABCD is equal to the length of the rectangle times the width. And the length of rectangle ABCD is AB, the width is BC. According to our definition, AB equals to A and BC equals to B. So in conclusion, found out that the area of rectangle ABCD equals to A times B, but we just right now found out that AB equals to 66, so we can write here that AB equals to 66. So in conclusion, we found out that the area of rectangle ABCD, the area that we are looking for, is equal to 66 square units. Okay, so I finished with the first method. In the next step, I'll present to you how to find out the area of rectangle ABCD according to the second method. Okay. In the second method, we know that all the angles inside a rectangle are right angles, so this angle equals to 90 degrees, this angle equals to 90 degrees, this angle equals to 90 degrees, and finally this angle, it is also equals to 90 degrees. As we did in the first method, we define side AB as A, we define side BC of rectangle ABCD is B, and I already explained to you that the diameter of this circle, it is also equals to BC. So here, write it down. We define the center of this circle is O. We join points O and P by a straight line. So point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of the circle that we define as R. We know that the diameter of the circle equals to B. Therefore, the radius of the circle must be equal to half of it, that is B over 2. So R equals to B over 2. We'll extend the radius PO by a straight line until it intersects with side AD of triangle ABCD. And we define the intersection point of the extended radius PO and AD as F. If we focus on quadrilateral AB, but before that, we have the radius OP that is drawn to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. So we'll focus on triangle ABF, on quadrilateral ABFP. In quadrilateral ABFP we have 1, 2, 3 right angles. I repeat again, in quadrilateral ABFP we have 1, 2, 3 right angles. Therefore the fourth angle, that is angle AFP, must be also equal to 90 degrees. So quadrilateral ABFP has here 1, 2, 3 right angles. Again, quadrilateral ABFP has 1, 2, 3 right angles. And any quadrilateral that has 3 right angles, the fourth angle must be also equal to 90 degrees, so this angle equals to 90 degrees. Therefore, inside quadrilateral ABFP we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral ABFP is a rectangle. Quadrilateral ABFP is a rectangle. Why? Because it has 4 right angles. Repeat again, quadrilateral ABFP is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, side AB equals to FP. Side AB equals to side FP. Okay, side AB equals to side FP, but according to our definition, AB equals to A. And from this equation, FP. From this equation, A equals to AB equals to FP, we will derive that FP is also equals to A. FP is also equals to A. Yeah, FP is equal to A. Likewise, if you focus on quadrilateral FPDC, this quadrilateral, in quadrilateral FPCD we have 1, 2, 3 right angles. Therefore the fourth angle, this angle, must be also equal to 90 degrees. We will define the touching point of the extended radius PO and the circle as point L. What is the definition of chord LP? Chord LP passes for the center of the circle, that is point O. Therefore, any chord that passes for the center of the circle must be the diameter of the circle. So LP is the diameter of the circle. We write it down. and P is the diameter of the circle, and the diameter of the circle is equal to B according to what we have already found out. We join points L and S together by a straight line. By joining points L and S together by a straight line, we created the here peripheral angle LSP. Peripheral angle LSP, this angle rests on LP, that is the diameter of the circle, and we have rule number 5 that relates to a peripheral angle that rests on the diameter of the circle according to rule number 5. Any peripheral angle that rests on the diameter must be equal to 90 degrees. So here peripheral angle AB rests on AB, that is the diameter of the circle, therefore peripheral angle AMB equals to 90 degrees. We can implement rule number 5 in our drawing, because in our drawing we have the peripheral angle PSL. Peripheral angle PSL rests on PL, that is the diameter of the circle, therefore peripheral angle PSL or LSP equals to 90 degrees according to rule number 5, okay? In the next step, we define angle LPS. This angle is theta, so this angle equals to theta. This angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta. Why? Because if you focus on the angle LSP, 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we'll focus on the right big triangle QFP. On this right big triangle, this angle equals to 90 degrees. This angle equals to theta, therefore this angle must be also equal to 90 degrees minus theta, exactly for the same reason that this angle equals to 90 degrees minus theta. So in the next step, we'll prove that the green triangle LSP is congruent, is similar to the big right triangle QFP. So I write it down. We'll prove that the big triangle FQP, this big right triangle, is similar to the green small right triangle LSP. Okay, we prove that the big right triangle FQP is similar to the small right green triangle LSP. So why those two triangles are similar to each other? First of all, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So you can write down that angle FQP, this angle, is equal to this angle, that is actually angle PLS. Repeat again, angle FQP in the big triangle is equal to angle PLS in the green right triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. So this angle, it is angle QFP. It is equal to this angle, that is actually angle LSP. Repeat again. angle QFP is equal to angle LSP, they are both equal to 90 degrees, therefore they are equal to each other. And finally, we have this angle that is a common angle that belongs to both triangles, so we can write down that this angle theta is equal to itself. So here angle theta can be defined as angle FPQ, and it is equal to itself. Angle theta can be defined also as angle LPS. And repeat again, angle FPQ equals to angle LPS equals to theta. So both angles are theta. So this states means that angle theta equals to itself. It's a common angle that belongs to both triangles. So we actually proved that the big right triangle FQP is similar to the small green right triangle LSP, according to angle similarity rule. So I write it down. The big right triangle FQP is similar to the right small triangle LSP, according to angle similarity rule. And for the fact that those two triangles are similar to each other, we conclude that the following relationship exists between their sides. We will conclude that FP over SP is equal to QP over LP. I'll repeat again and conclude that FP over SP equals to QP over LP. FP equals to A, so we substitute FP by A. SP equals to 6, so we substitute SP by 6. QP equals to 6 plus 5, that is 11, so we substitute QP by 11 over LP. LP is the diameter of the circle, that is equal to B, so we substitute LP by B. So in conclusion, we found out that according to equation number 1, A over 6 equals to 11 over B. Here we cross multiply this equation number 1, and we'll get that according to equation number 1, A times B equals to 6 times 11, that is 66. So AB equals to 66 according to equation number 1. And what is the area of rectangle ABCD? The area of rectangle ABCD is equal to the length of the rectangle, that is AB, times the width of rectangle ABCD, that is BC. Okay. AB equals to A and BC equals to B according to our definition. So in conclusion, we found out that the area of rectangle ABCD equals to AB, but we just right now found out that according to equation number 1, AB equals to 66. So we can write here that AB equals to 66. So in conclusion, we found out that the area of rectangle ABCD equals to 66 square units. We finished with the second method. In the next step, I will summarize the lecture. I will start with the first question, of course. So in the drawing, we have triangle ABC. Inside triangle ABC, we have a circle that is inscribed by triangle ABC. Side BC equals to 2 units. Angle ABC equals to 60 degrees. Angle ACB equals to 75 degrees. And our mission is to find out the radius of this circle that is inscribed by triangle ABC. So in the first method, we did the construction from point C, we drew perpendicular on AB. Then I copied the right green triangle DBC and we analyzed the right green triangle DBC. This is the right green triangle DBC that I copied from the original drawing. We know that the sum of the angles inside the right triangle DBC must be equal to 180 degrees according to the rule that the sum of the angles in a triangle is equal to 180 degrees. So which angles we have inside triangle DBC? We have this angle that is equal to 90 degrees plus this angle that is equal to 60 degrees plus the missing angle that we defined as x, In total, the sum of those two angles must be equal to 180 degrees. So 60 degrees plus 90 degrees is 150 degrees, and 150 degrees plus the size of the missing angle x, in total they must be equal to 180 degrees. We subtracted 150 degrees from this equation and found out that the missing angle x equals to 180 degrees minus 150 degrees, it is 30 degrees. So this angle equals to 30 degrees. You can write here that this angle equals to 30 degrees, that is angle DCB. Okay. Then we continue to focus on the right triangle DBC. The right triangle DBC, it is very easy to see from the drawing that sinus 30 degrees equals to DB over CB. Sinus 30 degrees equals to DB over BC. So sinus 30 degrees equals to DB over BC, but BC is 2, so we substitute BC by 2. So in conclusion, we found out that sinus 30 degrees is 1/2, and 1/2 equals to DB over 2. We multiplied this equation by 2 and found out that BD equals to 1 unit. Here, BD equals to 1 unit. We continue to focus on the right triangle DBC. On the right triangle DBC, cosine 30 degrees equals to DC over BC. Cosine 30 degrees equals to DC over BC. And cosine 30 degrees equals to DC over BC. Cosine 30 degrees is 4 to 3 over 2. And it is equals to DC over BC. BC is 2, so we substitute BC by 2. So in conclusion, we found out that square root of 3 over 2 equals to DC over 2. We multiplied this equation by 2 and found out that DC equals to square root of 3 units. Here, DC equals to square root of 3 units. Then we found out the size of this angle ACD. Angle ACD equals to 75 degrees minus 30 degrees, that is 45 degrees. Then I copied the right triangle ADC in a new page and we analyzed triangle ADC. This is the right triangle ADC that I copied from the original drawing. In the right triangle ADC, the sum of the angles must be equal to 180 degrees. This angle equals to 90 degrees plus this angle that is equal to 45 degrees plus this angle, the missing angle that we defined as x. In total, the sum of those three angles must be equal to 180 degrees. 90 degrees plus 45 degrees is 135 degrees, and 135 degrees plus the missing angle that is x. In total, they must be equal to 180 degrees. We subtracted 135 degrees from this equation and found out that the missing angle x equals to 180 degrees minus 135 degrees, that is 45 degrees. Okay, so this angle equals to 45 degrees. So, and we have the rule that in front of each one angles in the triangle, they are equal sides. So those two angles that are equal to each other, we have from inside, in front of this angle, we have side DC, in front of this angle, we have side AD. Therefore, those two sides that are located in front of equal angles must be equal to each other. That is to say, AD equals to DC. But we have already found out that DC equals to the square root of 3 units. So we can ideate that DC equals to the square root of 3 units, and from this equation AD equals to DC equals to the square root of 3 units, we will derive that AD is also equals to the square root of 3 units. AD equals to the square root of 3 units. Then we continue to focus on the right triangle, triangle ADC. On the right triangle, triangle ADC, we implemented the Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AC square equals to AD square plus DC square. AC square equals to AD square. AD is equal to 3, so AD square is equal to 3 squared, that is 3. Plus DC square. DC is square root of 3, therefore DC square is square root of 3 squared, that is also 3. So in conclusion, we found out that AC square equals to 3 plus 3, that is 6. We took out of this equation number 1, and we found out that AC equals to the square root of 6 units. Here AC equals to the square root of 6 units. Then I presented to you a new formula to find out the radius of any triangle that is inscribed, the radius of any circle that is inscribed by a triangle. The radius of a circle that is inscribed by a triangle will be equal to the area of the triangle that blocks the circle over the semi-perimeter of the triangle. Therefore, we can implement the new rule, that is rule number 7 in our drawing. In our drawing, we get that the radius of this circle that is described by triangle ABC will be equal to the area of triangle ABC over the semi-perimeter of triangle ABC. And the semi-perimeter of any triangle is the perimeter over 2. Okay, the area of triangle ABC, the radius of triangle ABC, the radius of the circle equals to the area of triangle ABC over the semi-perimeter of triangle ABC. And the semi-perimeter of triangle ABC equals to the perimeter over 2. So what is the area of triangle ABC? The area of triangle ABC here, it is equal to the base of the triangle that we took as AB times the height to the base, that is CD over 2. So it is AB times CD over 2. AB is 1 plus square root of 3. CD is square root of 3 over 2. This expression, 1 plus square root of 3 times square root of 3 over 2, is 2.366 square units. So the area of triangle ABC equals to 2.366 square units. What is the semi-perimeter of triangle ABC? It is equal to the perimeter that is AB plus AC plus BC over 2. AB is 1 plus square root of 3 units, AC is square root of 6 units, and BC is 2. And if you divide it by 2, you get the semi-perimeter of triangle ABC. This expression equals to 3.59 units. So in conclusion, we found out that the semi-perimeter of triangle ABC equals to 3.59 units. And the radius of the circle that is inscribed by triangle ABC equals to the area of triangle ABC over the semi-perimeter of triangle ABC. The area of triangle ABC equals to 2.366 square units, and the semi-perimeter of triangle ABC equals to 3.59 units. So the radius of the circle that is described by triangle ABC equals to 2.366 over 3.59, that is equal to 0.6589 units. Okay? Then I presented to you a second method to find out the radius of this circle that is inscribed by triangle ABC. The radius, here we define the center of the circle as point O. We defined the intersection point of tangent BC with this circle as point D. We join points O and D together by a straight line. Point O is the center of the circle. Point D is the point of the circle itself. Therefore, OD is the radius of this circle that is equal to R according to our definition. R Here the radius OD, it is drawn to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees, and this angle equals to 90 degrees also. Then we defined the point of tendency of tangent AB with this circle as E. We join points O and D together by a straight line. Point O is the center of the circle, point E is the point of the circle itself, therefore OE is the radius of this circle that is equal to R according to our definition. Here we have the radius OE that is drawn to the point of tendency, therefore this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule number 1. Then we define the point of tendency of tangent AC with this circle as F. We join points O and F together by a straight line. Here point O is the center of the circle. Point F is the point of the circle itself, therefore OF is the radius of the circle that is equal to R. Here we have the radius OF that is drawn to the point of tendency, therefore according to rule number 1, this angle will be equal to 90 degrees and this angle also equals to 90 degrees according to rule number 1. Then, actually I presented to you rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. Here we have tangent from the common external point P, we have tangent PA and tangent PB. And according to rule number 2, the lengths of those two tangents are equal to each other. That is to say, PA equals to PB. We can implement rule number 2 in our drawing, because if we focus on the common external point B, from the common external point B, we have two tangents to the circle, tangent BE and tangent BP, and according to rule number 2, they must be equal to each other. That is to say, BD is equal to BE. And if you focus on point C, from the common external point C, we have two tangents to this circle, tangent BD and tangent BF, and according to rule number 2, they must be equal to each other. That is to say, FC equals to CD. Then we proved that the green triangle is congruent to the orange triangle according to side rule. Why those two triangles congruent to each other? First of all, we just right now found out that BD in the green triangle is equal to AB in the orange triangle. In addition, we know that DO equals to EO because they are both the radii of the circle, therefore they are equal to each other. And finally, we have side BO that is a common side that belongs to both triangles, so BO equals to itself. Okay, therefore, actually proved that those two triangles can go to each other according to side rule. And from the fact that those two triangles can go to each other, we will conclude that those two angles are equal to each other. According to the rule, that corresponding angles in congruent triangles are equal to each other. Here, angle OBD in the green triangle is equal to angle OBE in the orange triangle. So if we define one angle as alpha, then the other angle must be also equal to alpha. But according to what is given us in the question, the sum of those two angles is alpha plus alpha must be equal to 60 degrees. Alpha plus alpha is 2 alpha, and 2 alpha equals to 60 degrees. We divided this equation by 2, and we found out that angle alpha equals to 30 degrees. So here angle alpha equals to 30 degrees, and here also angle alpha equals to 30 degrees. Likewise, we can easily prove that those two triangles can go into each other according to side rule. Exactly like we proved that the green triangles can go into the orange triangle, so I will not repeat on it. And because of the fact that those two triangles can go into each other, we derive that those two angles are equal to each other. Yeah, that is to say, angle FCO equals to angle OCD. So if we define one angle as theta, then the other angle must be also equal to theta. So here theta plus 2 theta must be equal to 75 degrees according to what is given as the question. Theta plus theta is 2 theta, and 2 theta equals to 75 degrees. We divided this equation by 2 and found out that theta equals to 37.5 degrees. Here theta equals to 37.45 degrees, and this again theta equals to 37.5 degrees. Then we focus on the green triangle ODB and the green triangle OBD. It's very easy to see that triangle 30 degrees equals to OD over BO. OD over BO. OD over BD. OD over BD. OD equals to R, so we substitute OD by R and we found out that triangle 30 degrees equals to R over BD. We multiplied this equation by d, and then we divided by tan 30 degrees, and found out finally that BD equals to R over tan 30 degrees. Likewise, we focused on the yellow triangle OCD, the yellow triangle OCD, triangle 37.5 degrees equals to OD over DC. Triangle 37.5 degrees equals to OD over DC. OD equals to R. We substituted OD by R. We found out that triangle 37.5 degrees equals to R over DC. We multiplied this equation by DC, and then we divided by triangle 37.5 degrees, and found out in conclusion that DC equals to R over triangle 37.5 degrees. So we have the values of DC and BD also. So, and what is the value of BC? BC equals to 2, but BC also equals to BD plus DC. Again, BC equals to BD plus DC. Here, BC equals to BD plus DC. So BC equals to BD, and BD is R over triangle 30 degrees, plus DC. DC is equal to R over triangle 37.5 degrees. R over triangle 30 degrees. We have here, we took R as a common factor from those two expressions. What is left from R over triangle 30 degrees after we took from it R as a common factor? What is left is actually 1 over triangle 30 degrees. And what is left from R over triangle 37.5 degrees after we took from it R as a common factor? What is left is actually 1 over triangle 37.5 degrees. So here we found out that 1 over triangle 30 degrees is 1.752, and 1 over triangle 37.5 degrees is 1.303. So 2 equals to R times 1.732 plus 1.303. And the sum of those two numbers is 3.035. So 2 equals to R times 3.035. We divided this equation by 3.035, and we found out that the radius of this circle that is described by triangle ABC equals to 2 over 3.035, that is equal to 0.6589 units. So in both methods we found out that the radius of this circle that is described by triangle ABC equals to 0.6589 units. We finished with the first question, then I presented to you the second question, and we solved the second question in two different methods. So in the drawing we have rectangle ABCD. Inside rectangle ABCD we have a circle that is described by rectangle ABCD. Chord PS equals to 6 units, line segment QS equals to 5 units, and our mission is to find out the area of this rectangle ABCD. So here, first of all the angles inside the rectangle are right angles, so those 4 angles are all right angles. And then we define side AB of rectangle ABCD as A, we define side BC of the rectangle as B, and the diameter of this circle is also equals to BC, that is B. Then we define the center of this circle as O. We join points O and P together by a straight line. Point O is the center of the circle. Point P is the point of the circle itself, therefore OP is the radius of this circle. And we have the radius that is drawn to the point of tendency, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. And if the diameter is equal to B, it means that the radius must be equal to half of it, that is to say that the radius of this circle equals to B over 2. Then we define the point of tendency of tangent DC with this circle as P as F. We join points O and F together by a straight line. Point O is the center of the circle. Point F is the point of the circle itself, therefore OF is the radius of the circle, that is equal to R. We have the radius OF that is drawn to the point of tendency, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. So we actually created here quadrilateral OPFC, and quadrilateral OPFC we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees according to the rule that sum of the angles in any quadrilateral is equal to 360 degrees. Okay, then I presented to you rule number 4. According to rule number 4, whenever you draw perpendicular from the center of the circle to any chord, it bisects the chord. So the center of this circle is point O, and we draw perpendicular on chord SP, therefore it bisects chord SP according to rule number 4, that is to say SM equals to MP. So if we define SM as X, then from this equation X equals to SM equals to MP, we will derive that MP is also equals to X. So here we have X plus X, that is actually equals to SP. Here X plus X equals to SP. X plus X is 2X, that is equal to SP, but according to what is given as the equation, SP equals to 6. So from this equation, 2X equals to SP equals to 6. We will derive that 2X equals to 6. We divided this equation by 2 and found out that X equals to 3. Here X equals to 3 units, here also X equals to 3 units. Okay, then actually from point Q, we draw perpendicular on BC. Again, from point Q, we draw perpendicular on BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and BC as T. Okay, so here I actually created quadrilateral OP edge T. Quadrilateral OP edge T. Inside quadrilateral OP edge T, we have 1, 2. Inside quadrilateral OPHT, we have 1, 2, 3 right angles. Therefore, this fourth angle must be also equal to 90 degrees. Therefore, we actually found out that inside quadrilateral OPHT, we have 4 right angles. And then any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we will relate quadrilateral OPHT as a rectangle. Okay, here quadrilateral OPHT is a rectangle. And we also know that the opposite sides of a rectangle are parallel to each other. That is to say, side OP is parallel to side HT. Again, side OP is parallel to HT. According to the rule that the opposite sides of a rectangle are parallel to each other. OP is parallel to HT. But here, HT is part of perpendicular QT. HT is part of perpendicular QT, and QT is as a perpendicular, it is absolutely a straight line. QT is a perpendicular, it is absolutely a straight line, so QT is a straight line. And we know that part of the straight line QT, that is HT, is parallel to OP. Okay, part of the straight line QT is parallel to OP. So if part of the straight line QT is parallel to OP, it means that the straight line or QT itself must be also parallel to OP. Okay, therefore the straight line QT must be also parallel to OP because of the fact that if part of a straight line is parallel to another straight line, then the straight line itself must be also parallel to the other straight line. Therefore QT is parallel to OP. And then I presented to you rule number 9, that the alternating angles between parallel lines are equal to each other. Those two angles are defined as alternating angles, and they are located between the parallel lines OP and QT, therefore they are equal to each other. That is to say, angle OPM is equal to angle PQT. So if we define angle PQT is theta, then from this equation we derive that the angle OPM is also equal to theta. This angle is also equal to theta. So those two angles are both equal to theta. Okay. And then we focus on quadrilateral QTDC. Inside quadrilateral QTDC we have 1, 2, 3 right angles, and any quadrilateral that has 3 right angles must be at least a rectangle, if not a square. So we relate quadrilateral QTDC is a rectangle. Why? Because it has 4 right angles. Here, quadrilateral QTCD is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, QT equals to DC. QT equals to DC. Okay, but here ABCD is also a rectangle, and the opposite sides of rectangle ABCD are also equal to each other. That is to say, DC equals to AB. DC equals to AB, and from this equation, QT equals to DC equals to AB, we will derive that QT is also equals to AB. Okay, QT is also equals to AB, but according to our definition, AB equals to A. AB equals to A, and from this equation, QT equals to AB equals to A, we will derive that QT is also equals to A. Here, QT is also equals to A. Okay, then we focus on the green, small orange, on the green right triangle OPM. I copy triangle OPM, in your page, and we analyze triangle OPM. This is the right triangle OPM that I copied from the original drawing. In this triangle OPM, cosine theta equals to MP over OP. Cosine theta equals to MP over OP. That is to say, cosine theta equals to MP, that is 3 units, and OP, so we substitute MP by 3, and OP is B over 2, we substitute OP by B over 2, 3 over B over 2, here we move 2 to the numerator, 2 times 3 is 6, we move B to the denominator, so in conclusion found out that according to equation number 1, cosine theta equals to 6 over B. Then we focused on the right triangle QPT. In the right triangle QPT, cosine theta equals to QP over QT. Cosine theta in the right triangle QPT, the right triangle, cosine theta equals to QT over QP. QT equals to A, so we substitute QT by A. QP equals to 5 plus 6, that is 11, so we substitute QP by 11. So in conclusion, according to equation number 1, we found out that cosine theta equals to A over 11. So we have 2 different expressions for cosine theta. Therefore, we created equation number 3 that states that cosine theta according to equation number 1 must be equal to cosine theta according to equation number 2. Cosine theta according to equation number 1 is equal to 6 over B, and must be equal to cosine theta according to equation number 2, that is equal to A over 11. Okay, so here, according to equation number 3, we found out that 6 over B equals to A over 11. We cross multiply this equation, we found out that AB equals to 11 times 6, that is 66. So AB equals to 66, and what is the area of rectangle ABCD? It is equal to the length of the rectangle times the width of the rectangle. The length is AB, the width is BC. AB is A, BC is B. So in conclusion, we found out that the area of rectangle ABC is AB. But we just like now found out that AB equals to 66 units. So we can write here that AB equals to 66, and in conclusion found out that the area of rectangle ABCD equals to 66 square units. We finished with the first method, then I presented to you how to find out the area of rectangle ABCD according to the second method. In the second method, we know that all the angles inside a rectangle are right angles, so those 4 angles are all right angles. We define side AB as A, we define side BC as B, and BC is also the diameter of the circle, so BC that is equal to B, it is also equal to the diameter of the circle. We define the center of the circle as point O, we join points O and P together by a straight line. Point O is the center of the circle, point P is the point of the circle itself, and for OP is the radius of the circle, that is equal to R. If the diameter of the circle equals to B, then the radius must be equal to half of it, that is to say it must be equal to B over 2, so R equals to B over 2. Then we extended the radius PO by a straight line until it intersects with side AD of rectangle ABCD at point F. So inside quadrilateral ABFP, we have 1, 2, 3 right angles. Here, this angle, we have the radius OP that is drawn to the point of tendency. Therefore, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. Then inside quadrilateral ABFP, we have 1, 2, 3 right angles. Therefore, the fourth angle, this angle must be equal to 90 degrees. Likewise, inside quadrilateral FPDC, we have 1, 2, 3 right angles. Therefore, this angle must be also equal to 90 degrees. Okay, so here we found out that quadrilateral ABPF has 4 right angles. Therefore, it must be at least a rectangle, if not a square. Okay, and we know that the opposite sides of a rectangle, so we relate to quadrilateral ABFP is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to FP. AB equals to FP. Again, we know that ABPF is a rectangle because it has 4 right angles, and the opposite sides of a rectangle are equal to each other. That is to say, AB equals to FP. But according to our definition, AB equals to A. So we can write here that AB equals to A. From this equation, A equals to AB equals to FP. We will derive that FP is also equals to A. Okay? Then, here we joined point L and S together by a straight line. In this way, we created peripheral angle LSP. Peripheral angle LSP rests on LP. And LP, called LP, is the diameter of the circle because of the fact that it passes through the center of the circle, that is to say from point O. Any chord that passes through the center of the circle must be the diameter of the circle, therefore LP is the diameter of the circle. Chord LSP rests on LP, that is the diameter of the circle, and any chord, any peripheral angle that rests on the diameter of the circle must be equal to 90 degrees according to rule number 5, so this angle equals to 90 degrees. So if you focus on the great angle LSP, this angle equals to 90 degrees. This angle, then we define this angle as theta, of course. So this angle equals to 90 degrees. This angle equals to theta, therefore this angle must be equal to 90 degrees minus theta, because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in the triangle, and especially in triangle LSP. Likewise, if we focus on the big right triangle FQP, this angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta. Exactly for the same reason, this angle equals to 90 degrees minus theta. Then we actually proved that the big right triangle FQP is similar to the small green right triangle LSP. Why those two triangles are similar to each other? First of all, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. And finally, this angle is a common angle that belongs to both triangles, so this angle equals to itself. So we actually proved that the big right triangle FQP is similar to the small right triangle LSP according to angle similarity rule. And from the fact that those two triangles are similar to each other, we conclude that the following relationship exists between their sides. We conclude that FP over SP equals to QP over LP. Okay, here FP equals to A, according to what we already found out, so we substitute FP by A. SP equals to 6 units according to what is given us to the question, so we substitute SP by 6. QP equals to 5 plus 6, that is 11, so substitute QP by 11, and finally LP is the diameter of the circle, that is equal to B. So substitute LP by B, and in conclusion, according to equation number 1, we found out that A over 6 equals to 11 over B. We cross multiplied this equation and found out that A times B equals to 6 times 11, that is 66. So according to equation number 1, A times B equals to 66. Then what is the area of rectangle ABCD? The area of rectangle ABCD equals to its length, that is AB, times its width, that is BC. Okay, AB equals to A, BC equals to B according to our definition. So we actually found out in conclusion that the area of triangle ABCD equals to AB. But we just right now found out that AB equals to 66 according to equation number 1. So we can write here that AB equals to 66. So in conclusion, we found out that the area of rectangle ABCD equals to 66 square units. In both methods, we found out that the area of rectangle ABCD equals to 66 square units. And in both methods, we found that the radius of this circle that is inscribed by triangle ABC equals to 0.65 at 9 units. Okay, thank you very much.